Hello. So today, in reference to the reading assignment on number theory and cryptography, we'll do our first. I'll do the most important things in more difficult things that reading assignment, namely extended Euclidean algorithm and the fast exponentiation algorithm. So first, extended Euclidean algorithm. So how can we think about this algorithm? So the input are integers a bigger than b bigger than 0. Output of the algorithm, because it's extended, we have two levels of output. First of all, it produces d, which is the greatest common divisor of a and b. So far, that's the Euclidean algorithm. Now, that's why it's called extended. So in addition to producing the greatest common divisor, GCD means greatest common divisor. I can put here greatest common divisor. In addition to producing greatest common divisor, it also produces two integers x and y, such that b is ax plus by. So in other words, the greatest common divisor can always be represented as a combination of the integers a and b. So ax plus by. Okay, so that's how to do it. And the technique of the algorithm is always divide. So we'll see when we execute the exact algorithm, but so probably at this moment doesn't seem too meaningful, but that's how it is. So always divide the big number by quote unquote small number with remainder divide the big number by the small number with remainder until the remainder gets to 0. This algorithm, until the remainder gets to 0. At that moment, the GCD is the last non-zero remainder. Non-zero remainder. And then x and y will be visible in the process. So let's do our first application of the extended algorithm on a concrete case. So I got a, so let's find, in this case, A equals to 1,270 and B equals to 997. So our task will be find the greatest common divisor of 1,217 and 997, and then express the greatest common divisor as a combination of those numbers A and B. So 1217x plus 997y. This is the GCD. Okay, so the format for this algorithm is a 4-column table. So remainder, quotient, x and y, a 4-column table. There's the head of the table, remainder, quotient, x and y. Let me annotate the columns. So the column of x is for the big number. But don't forget this, because I want you to, in the test, to put exactly in this format I just told you. So 1217 here, annotation. And for this one, the annotation is 997. So y stands for is the coefficient of the small number, and x is the coefficient of the big number. the first two rows, there's not really a row for the table. The first two actual rows of the table are data entry. So put a big number here, 1217. Small number is 997. And so far, at the beginning, we didn't do any division, so no divisions, yes or no quotient. And to initialize x and y, we initialize like an identity matrix of 1, 0 here and 0, 1. So every row has a reading. How do we read this row? 1217 equals to, look at the label, 1217 times 1 plus 997 times 0, right? 997 equals to 1217 times 0 plus 997 times 1. So this is the data entry. Now, so far the algorithm did not start yet. So let's start the algorithm. So always, like I said, divide the big number by small number with remainder until the remainder is 0. So how many times enter small number in big number? 997 in 1217 enters 1 time. Right. So quotient is 1. Right? Because 997 in 1217 enters 1 time. And the remainder, so let's subtract 1217 minus 997. What would be this one? 220. Then, how to update the values for x and y? So, look at the last quotient. So multiply by the last quotient the latest entries of x and y and subtract from the previous ones. So what we got here? 1 times 0 is 0, subtract 0 from 1, we get a 1. 1 times 1 is 1, subtract from 0 is a minus 1. How do you read this row? 220 equals to 1217 times 1 plus 997 times minus 1. And almost 1217 minus 997. Okay, so let's continue because the remainder did not get to 0. Divide the big, so what's the big number now? Big number is 997, small number is 220. How many times enters 220 in 997? Well, it enters 4 times. 4 times. Okay, so let's see. 4 times 220 is 880. Up to 997 is 117. Then update x and the y. Multiply and subtract. So 4 times 1 is 4. Subtract from 0 is minus 4. 4 times minus 1 is minus 4. Minus 4 subtract from 1 is 1 minus 4 is a 5. So 117. 4 is the quotient, minus 4 is x, 5 is y. Okay, the remainder did not get to 0 yet, so we continue. Small number now is 117, big number is 220. How many times enters small number in big number? Well, it enters, it cannot enter 2 times, so 1 time. Right? And the remainder is from 117 to 220, 83 is 103. 103. Now let's update the values for x and y. Multiply and subtract. 1 times minus 4 is minus 4. Subtract minus 4 from 1 is 5. Subtract 5 from minus 1 is minus 6. So I got a 5 and a minus 6. Right. Next, so the remainder did not get to 0. Let's continue. How many times enters 103 in 117? Well, 1 time only. The remainder is 14. So notice that in the column, the remainder is always we have a decreasing pattern. That's why we hope the theory says that eventually get to 0. So again, 103, 117 enters 1 time. The remainder is 14. Now multiply and subtract. We'll get a minus 9 here and 11. Right? Okay, remainder is not 0 yet. So let's continue. How many times enters 14 in 103? 7 times. 7 times 14 is 98. 98 to 1, from 98 to 103 is 5. The remainder is 5. Multiply and subtract. 7 times minus 9 is minus 63. Subtract minus 63 from 5 is 68. 7 times 11 is 77. Subtract 77 from minus 6 is minus 6 minus 77 is minus 183. Sorry, minus 83, no, minus 183. So, sorry, 77. So, minus 6, minus 77, minus 83. Minus 83. Right. Again, let's continue. Small number is 5, big number is 14. How many times enter small number in big number? Enters 2 times, right? Remainder is 4. Multiply and subtract. 2 times 68, 136. Subtract 136 from minus 9 is minus 9, minus 136 is minus 145. What about the other one? Multiply and subtract. 2 times minus 83 is minus 166. Subtract minus 166 from 11 is 11 minus 166 is 11 plus 166 is 177. We're almost there. Now, at this moment, the small number is 4, big number is 5. How many times enter small number in big number? 1 time, remainder is 1. Multiply and subtract. So subtract minus 145 from 68. It is 213. Because it's 68 minus 145 is actually 68 plus 145. 140 plus 6 is 200 and plus another 13. 8 plus 5 is 13. Now subtract 177 from 183. So it's minus 83 minus 177 is minus 260. Right. So 213 and minus 260. Okay, at this moment, small number is 1, big number is 4. How many times enters small number in big number? 4 times. Remainder is 0. At this moment, that's our clue that the algorithm ends. So at this moment, algorithm, because we got 0 here, EEA algorithm, extended Euclidean algorithm, ends here. So basically, we don't really care about anything else. We stop the algorithm, and then the GCD. So there's a conclusion. GCD of 2017 and 997 is last non-zero remainder. Last non-zero remainder. Last non-zero remainder is the GCD. And X and Y are exactly what we did here. This is X, this is Y. So X is 213 and Y equals to minus 26. So this amounts to what? GCD can be expressed as a combination of the two numbers A and B with coefficients 213 and minus 260. So GCD is 1. So D equals to 1 equals to 1217 times X times 213 plus 997 times Y, so times minus 260. Now you can calculate for yourselves. So you multiply with the calculator of 1217 times 213 minus 997 times 260, and that, believe it or not, you'll get exactly 1, right? So that's the idea of the extended algorithm. So another application of the extended Euclidean algorithm, since we got it here, let's try to do it right now. Extended Euclidean algorithm is good to find inverses. So good for inverses. Since we got here inverses modulo M. Modulo modulus, right? So as an application of this algorithm, somebody may ask, find the inverse of the small number modulo the big number. So 997 inverse modulo 1217. So in other words, what does it mean, the inverse of 997 modulo 1217 means a number in the ring of integers modulo 1217 with a property that multiplied by 997 modulo 1217 is 1. So how to find the inverse? Let me use the colored line here. The inverse of 997, go down the column of the small number until we get to the last value of y here. So the inverse of 997 inverse equals to minus 260. But what kind of minus 260? We have to do a little bit more. Minus 260 modulo 1217. In modular arithmetic, these are the easiest things at the beginning of the reading assignment. I'll not do the easiest thing. This you can read. So how to make a negative number positive? So negative, there are no negatives and positives modulo n. They are only negative looking, positive looking. How to make a negative looking number positive looking? Keep adding the modulus until for the first time we get positive. So this is the same to make it positive. Minus 260 plus 1217 equals to, I got it here, is 957. So the inverse of 997 is 957. So what does it mean? 997 times 957. The product in the number and its inverse is 1. But what kind of 1? Modulo 1217. That's the meaning of the inverse. So 997 inverse is 957 because if we multiply 997 with 957 and find the remainder and divide it by 1217, we get exactly 1. So that's a very powerful application of the extended Euclidean algorithm, which allows us to find inverses modulo big numbers, right? And there is also the theorem of Lamé. So number of divisions in the Euclidean algorithm is almost 5 times the number of digits of the small number. So for example, if the small number is 3 digits, right? 3 digits. How many lines in the Euclidean algorithm should they expect? At most 5 times 3 is 15. So how many lines we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 lines, right? So I put here this one 10, which is the finish line. Anyway, it is at most 15, right? Okay, so that's basically the extended Euclidean algorithm. Okay, so now let's move on. Another important algorithm, which is the pillars of cryptography. The pillars of cryptography we'll discuss later are extended Euclidean algorithm and fast exponentiation. So let's discuss now about fast exponentiation. Fast exponentiation. So it allows us to calculate a huge exponential but modular calculations. So let me introduce it in a little bit of the theoretical introduction. For example, let's see, we want to calculate a to the power 100, right? What's the traditional way? We calculate 1, we get multiplied by a, we get a, multiplied by a, we get a squared, multiplied by a, we get a cubed, and so on, a to the power 4, etc., 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 until we get to a to the power 100. So how many multiplications we did in this process? We get from a to the power 0, which is 1, to a to the power 1, 1, 2, 3, all the way through 100. We get 100 multiplications. There's a multiply the hard way. What will be the fast exponentiation? So compare these two. Fast exponentiation is also called repeated squaring. Repeated squaring. So let's see. So we'll start with a, right? This a to the power 1. Square it. So this idea, this operation is square it. We get a squared. Square it. with a to the power 4. Square it with a to the power 8. Square it, a to the power 16. Square it, a to the power 32. Square it, a to the power 64. And that's it. We don't want to go past 100. The planned exponent is 100. So repeated squaring, how many multiplications we did is we got 1, 2, 3, 4, 5, 6 multiplications by squaring. Okay, but it's not enough. So now we want to calculate a to the power 100. So we want to write 100 as the sum of those exponents. The exponents are 1, 2, 4, 8, 16, 32, 64. Right? So that's a greedy algorithm. So it's writing 100 in base 2 essentially. So 100 equals to 64. What's left? Left is 36. So what's that? So that's the greedy algorithm is what's the biggest chunk you can bite from 100 by using those possible bites. 64, right? The leftover is 36. The maximum bite you can get at this moment is 32. So 32 I can bite out of 36. What's the leftover is 4. And I just get the 4 by itself, right? 64 plus 32 plus 4. Okay, so we got here. So once we got this one, that's very important too. So we get a to the power 100. What would be a to the power 100? It's a to the power, because we wrote 100 as the sum of those exponents, is 64 plus 32 plus 4, which would be a to the power 64 times college algebra. Exponential of a sum is the product of the exponentials. A to the power 64 times a to the power 32 times a to the power 4. Which it is what it is. How many multiplications you need to get to multiply 3 numbers? We can say multiply this together, 1 multiplication, and the result multiplied with the other one, we get 3 multiplications. So overall, to calculate by this method, a to the power 100, we only need 6 from the repeated squaring and 3 from the other step, 9 multiplications compared to 100 multiplications. So there's a big increase in efficiency, right? So that's a very important algorithm which allows us to calculate fast modular exponentials. Okay, let's do our first application. Let's do calculate example. Calculate 511 to the power 320 modulo 543. Okay, so in this case, the fast exponential algorithm is 3 steps. First step is the fast exponentiation. So it takes the form of a table. So step 1, step 1 is a repeated squaring. Repeated squaring. The form is the form of a table. What's the table? Only with 2 columns in this case. Just do repeated squaring. Simple is enough. Okay, now what's the label for the first column is k versus 511 to the power k, but everything is modulo 543. That's how they get in the first column is k. K is the exponent. In the second column is the power. 511 to the power k modulo 543. 543 is the modulus. Okay, so let's initiate. if k equals to 1, 511 to the power 1 modulo 543 is just 511. It's a no-brainer. 511 to the power 1 is 511. Now, it's very important to keep in mind how to advance in every column. Right? In the left column, we double. So why we double? Because when we square, it's called repeated squaring. That's why it's called repeated squaring. When we square, the exponent doubles. Then we square the previous result. We double on the left column, we square modulo 543. So square to the power 2 modulo 543 in the second column. So two distinct way of operating are in each of the columns. In the first column we double, second column we square modulo 543. Okay, so square it. So double it, so get a 2. Now, what we got here? 511 times 511, so 511 squared modulo 543. So you need a calculator, by the way, you need a calculator for those things. So 511 squared, let me put the result. I got the result here, 481. So you need calculator. You use a calculator in all those levels, all those steps, right? Double, we get a 4 here. What we put here? 481 squared modulo 543. So square the previous item. So we'll get 43. Double, we get an 8. 43 squared modulo 543 will get a 220. Double, 16. Square 220 is a big number, but use calculator. And 220 squared, and then that's a big number, and divide by 543 will remainder with the calculator, and we'll get 73. Next, double 32. 73 squared modulo 543 is 442. Double 64. 442 squared modulo 543. Everything is modulo 543. So everything is mod 543. Okay, so what we got here? So square the previous item. 442 squared modulo 543 is 427. Double 128. 128 square 427 modulo. It's a big number. 427 is square. 427 squared. So 427 times 427. It's a big number, and then I use calculator to divide by 543 and to get the remainder. 427 squared is 424. Okay. Then double again, 256. 424, what we got here? Square the previous item. 424 squared is 43. And we are done here because we don't want to get past the exponent, the planned exponent 320. So this is step one of the fast exponential algorithm. Step 2. Step 2 is a greedy algorithm. So greedy subroutine, right, in a sense. So write down what's the planned exponent. 320, write as a sum of items in the left column, right? So that's the greedy algorithm. What's the biggest quantity you can byte from 320, and the possible sizes of the bytes are numbers in the left column. It's 256. 256, that's how the greedy algorithm works. 256 plus what's the leftover? If we take out 256, we'll get a 64. Right? So that's what is on the table at this moment, 64. How much time can get out of 64? The possibilities of what we can take are items in this left column. Of course, can take 64 at once. So plus 64. And we are done with step 2. Step 2 is very trivial. As a result of the greedy algorithm. Step 3. step 3, I like to call step 3 is the college algebra step. College algebra step, why we call it college algebra step? Because the exponential of the sum is the product of the exponential. That's the college algebra stuff. So, what was our plan? 511 to the power 320 equals to 511 to the power. Use the previous step. 320 is 256 plus 64. So 511 to the power 256 plus 64. But exponential of the sum is the product of the exponentials. Is 511 to the power 256 times 511 to the power 64. By the way, everything is a modular exponentiation. It's not the huge numbers we expect. So now how do you read 511 to the power 256? 511 to the power 256, use the table. So this will be 43 times 511 to the power 64. What will be this one? 427. So that's a very easy calculation. It's a use calculator to multiply 43 times 427 is a big number. This big number divided by the modulus 543, but everything is modulo. Everything is mod 543. Everything is mod 5. So we got 43 times 427, and the result equals to, after doing this stuff with the calculator, is 442. That's the answer for the partial exponentiation. Okay, so these are the most important algorithms in lithography, actually. So it's a necessary condition to be performant in cryptography to know those basic algorithms. Extended Euclidean algorithm, as we've seen, it can be used quickly to find inverses modulo m, modulo modulus, and there's a fast exponentiation, which they can be used to raise to large powers, modulo m. Okay, now you go ahead and read the reading assignment. That's very important because reading assignments are more things. So let's go ahead and read the reading assignment number 1, number 2. So next time we need to do some RSA cryptography and so they complete all the reading assignments in number theory cryptography. Okay, and also start working on the homework, like the latest homework. Okay then, so I will see you tomorrow then.